Now that I've defined all of those different terms that we're going to run across, the extrema, local extrema, absolute extrema, I want to talk about the guidelines for finding those extrema on the closed interval. One thing we're always going to do is we're going to check those endpoints, because those endpoints, as I said, could be maxes or mins. So we're going to definitely check our endpoints. Then we're going to find the derivative, and we're going to determine what x's are equal to 0 or where it does not exist. All of those cases where the derivative equals 0 or does not exist are where those extrema occur. So we need to do both of those things in order to determine our extrema on the graph. What I'm going to start with is just pictures. So we're going to find the value of the derivative if it exists at each indicated extrema. So we're first going to go ahead and look at this point right here at -1, 0. We're going to determine the derivative of that. The derivative of this point, so this derivative at -1, it does not exist. And that's all we're going to state right now. It does happen to be an extrema because the derivative does not exist. This one up here, we're going to determine the derivative of -2/3 to be equal to 0. Notice how the slope of the tangent line to the curve is 0. On the next example I have here, we're going to look at 0,4 and determine what is going on with the derivative at 0,4. I can see at 0,4 this is a corner, and I know that the derivative at 0 then does not exist because derivatives do not exist at corners. So when you're asked to just find the value of the derivative, that's all it's really seeing is that you can see whether it does not exist or n equals 0. On this problem, we are asked to find or to approximate the critical numbers of the function shown in the graph. We're going to determine whether the function has a relative max, a relative min, an absolute max, an absolute min, or none of these shown. So number 8 is kind of a strange example. It is actually talking about an open interval. So we are not going to be checking the endpoints because it's an open interval. Had these been closed in dots, we would have said, oh yeah, this has a minimum here and a maximum here, and those would happen to both be absolute mins or maxes. But since we are talking about an open interval, we do not check the endpoints, nor do we say that there's a max or a min at those. So the only approximation that I can make is this one, that there is a critical number at, so there is a critical number at x equals 0. And that's because, I'll put that, because the derivative at 0 is equal to 0. Is it a relative max or a relative min or an absolute max or an absolute min? No, it is not any of those things. It's not the highest point, it's not the lowest point. It actually is just a critical number. The function continues to increase throughout there. So there is actually none of these in this function. The second one we're going to look at is another open interval. I'm supposed to approximate the critical numbers. It looks like, again, I have another open interval, so I won't be checking the endpoints, but it looks like there is the slope right here. So the derivative at 2 is equal to 0. That would be a critical number. And right here, the slope of the tangent line of the curve is 0. So I'd say at 5 is equal to 0. So there's critical numbers at x equals 2 and 5. Now, we need to determine if those are relative max or mins. This one is none. It's nothing. However, at 5, this is considered the highest point of the function, so it is considered its absolute max. And I'll abbreviate that a little bit.